All right, now we are going to forge onward into the reduction and oxidation portion of Chapter 19, beginning with reductions with hydrogen gas. So, what have we gotten through so far? It's been a mishmash. We learned how to make Grignards and organolithiums, but that was introduced in Chapter 18 by me. So that's taking the alkyl halide, adding the metal to make the organometallic. And then we've kind of focused on trying to understand how to approach syntheses, throwing in some new reactions along the way, but looking at a target and recognizing 1,2 positioning, 1,3 positioning, 1,5 positioning, and using that as a clue as to what kind of chemistry we might need to use. And then lastly, we looked at the strategy associated with using protecting groups. So now we're going to focus on these reductions with hydrogen gas, which follows pretty nicely from some reduction chemistry we've already learned. And that is the reduction of carbonyls, aldehydes and ketones, by these hydride reducing agents, lithium aluminum hydride and sodium borohydride. And I should definitely add in, this includes the NADH biochemical hydride reducing agent that we have working in our bodies. So these all amount to H-, and we sure know by now that aldehydes and ketones are electrophiles, and so this is the expected electron movement that we see. Addition of that H right there gives us the alcohol, but we saw that that hydride reducing agent isn't going to work to go from here to here, because I sure can't add H- and kick out OH- to get here. So that's where we had to learn about the Wolff-Kishner, the Clemenson, and the use of Raney nickel. Now we're going to look at a new reducing agent, not H-, but hydrogen gas. So it's really straightforward if you look at what's going on. All of these multiple bonds can simply add H2 right across that multiple bond. So if I just focus in on what's going on here, across the carbonyl, 2 hydrogens gives me an alcohol. Across the alkene, 2 hydrogens gives me the alkane. And here's the alkyne. Add once to get the alkene, add twice to go all the way down to the alkane. So note that these are all reductions, and note that in this particular case we have 2 steps in going from an alkyne all the way down to the alkane. We can reduce these carbons down to -1 or take them all the way down to -2. So the deal is we can add hydrogen across a double or triple bond, and we're going to look at alkenes and alkynes first. But the problem that doesn't make a lot of sense is that we know triple bonds, double bonds, they are weak pi nucleophiles, and Lord knows that hydrogen gas is not an electrophile. It's not a nucleophile either. It's not nothing. So the problem is nothing will happen unless you add a transition metal catalyst. So there's 2 parts to these transition metal catalysts. First of all, the metal is the key point. That's where the chemistry happens. So the unfortunate problem is these transition metal catalysts are pretty dang expensive. So we need palladium, platinum, nickel. Palladium's far and away the best. Platinum's good too, but they're super expensive. So we maximize our working bit, the metal surface, by spreading it on an inorganic solid. That's called our support, and that's something like calcium carbonate, which is basically chalk, barium sulfate, or just graphite carbon. So you have very finely divided particulate here, upon which you just deposit just an atomic layer or two of the metal. So this depiction shows you this green thing is the support, so that's the barium sulfate or whatever your inorganic, cheapy inorganic support is. Just a few atoms of your metal, and basically what happens is the hydrogen and your alkene or your alkyne adsorb onto the surface of the metal, and then almost like Tinker Toy chemistry, those hydrogens pop onto the double or triple bond and release the product from the surface. So the take-home message here is there's no nucleophile, there's no electrophile, there's no electron movement. If you want to learn how this really works, take the synthesis class next fall, because it's all about organometallic chemistry. So there's more to it than a simple little cartoon of the metal surface, but for now that's fine with us. We'll stick with that cartoon and just understand that when I have hydrogen gas in the presence of my catalyst, then now you see it, now you don't. The hydrogen gas readily adds to your double bond and goes down to the alkane. This is an industrial example of synthesis of a drug called Propecia. If you don't know about Propecia, it is a hair loss remedy. Like if you've heard of Rogaine, Propecia is a competitor. So, what about alkynes? Well, it stands to reason that if this is a surface phenomenon, which we know that it is, then it stands to reason that the hydrogens would both have to be delivered from the same side. So you must get cis addition. And therefore you end up with the Z double bond. However, in this reduction, we're going from 0 and 0 to -1 and -1. It's evident that it can keep going. If I can reduce alkenes with hydrogen gas, which we just saw on the previous slide, obviously this whole reduction of an alkyne can go all the way down and reduce my carbons all the way down to the -2 oxidation state. So, how can I prevent this over-reduction? Because, let's face it, sometimes you want to stop here and have some selectivity in the reduction of your alkyne. So, there you go. You just poison your catalyst. So poisoned catalysts are how you reduce the activity of the catalyst and get the alkyne to stop at the alkene stage. So kind of breaking down the structure of your catalyst again, the whole piece consists of the active metal, palladium, the cheapy support upon which it's evaporated onto, and then the poison is typically quinoline. Some older references might tell you about lead as a poison, but lead is rarely used anymore. This particular combination is called Lindlar's catalyst. This is quinoline, and basically all quinoline is doing is coordinating to the metal and making it less reactive. So, just so you know, I may or may not refer to it as Lindlar's catalyst. I may or may not write down palladium, barium sulfate, quinoline. So you need to recognize these as the poison catalyst that allows you to stop at the alkene stage. So here's two examples. Here's a nice long chain fatty acid ester. It has a triple bond in it. As long as I'm using my poison catalyst, then I have no problem stopping this at the alkene stage. Okay, it goes no further. But without the poison, the reaction proceeds all the way to the alkane. Just so you know how we run these reactions, since hydrogen is a gas, you typically either put it in a pressurized container or bubble hydrogen gas through the reaction mixture, or put a balloon full of hydrogen on top of your flask. So there's no way you can actually add one equivalent of hydrogen. It's too difficult to control, and you'd end up with a mixture of the alkene and the alkane anyway. So to stop at the alkene stage, you must use the poison catalyst. Let me point out then that on page 944 there's an example that points out a poison catalyst that is not in fact a poison catalyst because they didn't add the poison. So you might want to take a look at that and make a note of that there needs to be quinoline in that particular example for that to stop at the alkene stage. Okay, so other considerations with respect to these hydrogenations. Well, these are pi bonds too. A nitrile, pi bonds. They'll all reduce with hydrogen gas. It works like a charm. So if I have this aldehyde, hydrogen gas, catalyst, in this case I didn't show the support, but a very common support for platinum is just platinum on carbon. There you go. You've reduced it by adding these two hydrogens. Works very well. But not all functionality is equally reactive. So if you look at table 19.3, you'll see that certain functional groups, for example, esters and amides, well, they'll react with the hydrogen gas and under catalytic conditions, but it's slow. So that's actually kind of handy because number one, we already know that we can use our hydride reducing agents that are nucleophiles to reduce those more stubborn functional groups. So lithium aluminum hydride will reduce anything, amides, the nitriles, etc. So this works great for the more reactive functional groups, but we might as well use the elephant gun here for the things that are a little bit more stubborn. Furthermore, this allows us selectivity because obviously there are a lot of functional groups that can be reduced, and if I'm just going to throw hydrogen in there, bubble hydrogen gas through my reaction mixture, how am I going to control which gets reduced? So here are a couple of examples. Obviously, if I'm looking at trying to reduce out one of these double bonds, this is the one that gets reduced. This one is left untouched. The reason here is because there's a big difference in the sterics here and here. Remember that these have to actually adsorb on the surface of the metal. This is really quite crowded. It's a lot easier for this tail to sit down on the palladium or nickel surface and add the hydrogen. So when it comes to a monosubstituted versus a trisubstituted double bond, there's no problem in selectively reducing this monosubstituted alkene. Similarly, if we go back and look at this example we saw earlier, this is Propecia again. Well, like I said, there is a lot of functionality that can be reduced here. This is what we want to reduce, but here's the amide. We can even reduce the carboxylic acid. These are all in high oxidation states that could be potentially reduced down to the alcohol or to the amine. But because with the use of hydrogen gas, the alkene is much more reactive, I have no problem just taking out that double bond. Note this is a tri-substituted double bond, so it's going to be a little more reluctant to undergo reduction. I do have to go up to 60 degrees, and it takes 3 hours, but still it is more reactive than either the carboxylic acid or the amide. So selectivity is very, very possible by judicious choice of your reagents. So sterics up here and just the general reactivity of the functional groups in the second example allow you to control where the reduction takes place. And then we have the joke. Unfortunately for you, it's an Sven and Ole joke. So Ole says, "When I die, I want to be buried at sea. Just because Lena keeps saying that when I die, she's going to dance on my grave." Yeah. Okay, that's all for reductions. Next up, oxidations.